to Session 5 of Unit 5. This session will introduce you to the various principles of all the gas-filled counters in ion chambers for radiation detection. By the end of this session, you should be able to explain how gas counters work. The ionization that is produced by ion chambers by a single particle is very low to be detected except for alpha particles. However, these ions that are formed multiply greatly and can be determined. We shall be discussing some common forms of gas ionization counters in this slide and in subsequent sessions. The first one we shall be looking at is the Geiger-Müller counter. The Geiger-Müller counter is the most common device used in the detection of radioactive contaminations. So the Geiger-Müller counter uses gas-filled tube with a central wire at high voltage to collect ionizations produced by incidented radiations. The Geiger-Müller counter can be employed to detect beta particles, alpha particles, gamma radiations, although it cannot distinguish between these various radiations. And it's good to note that the Geiger-Müller counter is often very portable and so can easily be carried around. Let us look at the efficiency of the Geiger-Müller counter for detecting radiations, and this depends on four factors. One is the type of radiation. So what type of radiation are we determining? Then the energy of the radiation. What is the energy of the radiation that is being determined? Also, the amount of activity in the source, so in the radioactive material. Then also the direction of the source relative to the instrument detector active area. So is the detector's active area close to the source of radioactive material? The Geiger-Müller counter is much higher for detecting beta particles than it is for detecting gamma rays. And this is because the beta particles do not travel far. So if they are able to enter the active portion of the meter, they have high probability of interacting and being detected. The gamma rays, on the other hand, they have higher energy, so they enter the active portion alright, but they may exit the active portion without interacting. Another form of the ionization counter that we shall be looking at is the ionization chamber. It is also portable as the Geiger counter. The ion chamber is used to measure the rate of radiation exposure. So the ion chambers are used when there is a measurable exposure or potential for measurable exposure to X-rays and gamma rays. The ability of the ion chamber to measure the exposure rate from a radionuclide is based upon the ability of the emission to reach the active portion of the meter and the energy of the emission. So the ion chamber is a gas-filled space between two electrodes. The electrodes are usually arranged parallel to each other. The electrodes, which are cathodes and anodes, are arranged parallel, as I said. The cathode acts as a hollow cylinder, and then the anode acts as a thin wire in its center. In this way, the chamber is able to record radiations that reach it from the outside. Next is the proportional counter. It is similar to the ionization chamber, and it helps to distinguish alpha and beta particles, and also distinguish between identical particles of different energies when different forms of primary ionizations are produced. The proportional counters are also used to detect neutrons. Next is the scintillating counting technique. It was developed in 1908 by Rutherford and Geiger. A scintillation detector is often portable. The scintillation detector's active portion for detecting radioactivity is a solid crystal with which the radioactive emission must interact. Scintillators can be made in different sizes, and the thickness of the scintillator determines its ability to absorb and detect certain radiations. The scintillating counting technique is reliable for counting alpha particles by observing visually the flashes of luminescence produced in a thin layer of zinc sulfide by the alpha particle. It is also used to detect gamma rays and also high energy beta particles, since medium and low energy beta particles cannot penetrate the crystals, that is the scintillator, and so they cannot interact. Now let's look at sizes of scintillators. So we have a thin scintillator, and is the best for low energy gamma rays and high energy beta particles. So this is how the thin scintillator works. The ray or particles will be absorbed within the thin scintillator, and it will produce a light which will pass through this scintillator, and then it will allow the gamma rays to be detected. Another size of the scintillator is the thick scintillator. This scintillator is thick enough to absorb the gamma rays, but not too thick to prevent the light that is produced from passing through to the detector. A thick scintillator is mostly the choice for radionuclides emitting high energy radiations, and it's not good for low energy radiations because the gamma rays may be absorbed by the scintillator, but the scintillator may be too thick for the light that is produced to pass through them to be detected. Let's look at another kind of detector, which is the counter, another form of counter, which is the liquid scintillator. They are mostly used for the measurement of beta emitters and alpha emitters. So the sample to be analyzed is dissolved directly in liquid scintillator solution, and a light output measured by photomultiplier tube. There are some other forms of these counters, which are the gas scintillator and then the solid scintillator. So I've attached this self-assessment question for you to try your hands on.